So now we're going to go into more detail with conservative vector fields. So, first of all, uh, let's just recall what a conservative vector field is. So we had that a conservative vector field is a vector field that arises as the gradient of some potential function. So we have this kind of expression, right? So if capital F is the gradient of little f, then capital F is a conservative vector field. And we had the property that conservative vector fields have this cross partials property. Okay, so that was one way that we could identify whether a vector field is possibly conservative, although we had this issue where just because it satisfied the cross partial property, it doesn't necessarily need to be the case that the vector field is conservative. And we'll go into that detail, or that example in more detail. That is the vortex field that is this subsection that I have here. Okay, well, let's start with what I have written here. So first of all, a bit of a addition to notation. We have this kind of integral with a circle around it, and this is sometimes called a contour integral because you're integrating over C, which is some contour. But specifically, when you have this circle, what this usually means is that the curve C is actually closed. And recall that closed means that you have I'm trying to make it a little bit thicker. Okay, come on. Closed means that your curve ends up being a loop, right? The two endpoints are the same point in your parameterization. Okay, so that's why we have a little circle there that kind of represents that fact that the curve is closed, that the ends meet up. All right. Now, these two pictures are serving to illustrate the following theorem, which is sometimes called the fundamental theorem for line integrals, sometimes called the fundamental theorem for conservative vector fields, but I'll be using FTLI to abbreviate, and I believe that the OpenStax book also calls it the fundamental theorem for line integrals. So yeah, these two pictures kind of help to illustrate the two parts to this theorem. All right, so first of all, we assume that our vector field f is conservative, meaning it is the gradient of some potential function. Okay, then what that says is you can instead, so recall that how I mentioned we compute line integrals back in I think it was 6.1, was it? No, 6.2, line integrals. The line integrals had to do with utilizing the parameterization. So you had this kind of property that this line integral, vector line integral, expanded out based on the parameterization that you had to be of this form. Dot product with r prime of t dt. And both of these are vectors. So you had this kind of expression which allowed you to compute the line integral, right? Which requires you to use the parameterization. Now, what this is saying specifically is that if your vector field ends up being conservative, you don't need to resort to this formula. You don't need to plug into the parameterization and take an integral. In fact, you don't even need an integral at all. What you need are the potential function f, and you need the two endpoints of the curve, p and q, or what I'm calling them. And then the line integral ends up just being evaluating at q and at p and subtracting the two, which is really analogous to the fundamental theorem of calculus. So what the fundamental theorem of calculus said was that if you're able to find an antiderivative capital F, right, you would then evaluate at the endpoints, which is just f of b minus f of a. And so this is really like the fundamental theorem of calculus part 2. This property is very much analogous to this one. Okay. And then moreover, note that when we use this formula, we don't factor in the specific path itself, the path between point P and point Q. So what we say is that f is path independent. The vector field is path independent. So line integrals that you compute over this vector field. I guess this should actually be in bold. That's a bit of a typo. So line integrals that are computed over this vector field are path independent. You don't need the path itself. You just need the two endpoints of the path, and then you're able to evaluate the line integral in that way. You only need to plug in at P and Q in this picture. Okay, and as a consequence of that, of part A, you immediately get part B, which is if you then have that 2 points, P and Q, are the same point, meaning that the curve C that you're integrating over, if that is a closed curve, if that is a loop, then the line integral, the contour integral over that curve C, that's just going to be 0, which follows immediately because, well, it ends up being little f of P minus little f of Q, right? So it's little f of, well, okay, I should reverse the way I'm writing it, little f of Q minus little f of P. Well, Q and P are supposed to be equal, and so that ends up being equal to 0. So it's immediate consequence of those things. I've written a little bit more in detail of how this proof works. It's actually quite understandable. We've gone through all the ingredients for it, and it's neat that it's there. But I don't think it's necessary to really talk through this. It's there if you want to read it. Okay. Oh, this still doesn't like to scroll. Okay. Right. So now an example. So suppose you have a vector field, like so. First of all, I'm just going to tell you what the potential function will be for this. So you just have to verify that it's correct. Soon we'll get to answering the question of how do we determine the potential function for just a given vector field. And I have 2 examples for that. It just ends up being about integrating and making sure that the functions all match up. But here we start by just verifying that it is a potential function, and then we evaluate the line integral over some curve, which the curve itself is not specified, but the endpoints are, and that's all we need because this vector field is conservative. Okay, so the way to check that this potential function works is we take the gradient of it. So we take the partial derivative with respect to x and y and z. So partial derivative with respect to x will give you this quantity. You can check that. Partial derivative with respect to y will give you this quantity, right? It's only coming from this term. And partial derivative with respect to z is only coming from this term, gives you x. And so therefore that reconstructs the vector field capital F, which shows that capital F is conservative. Okay, and now this line integral then, we can appeal to the fundamental theorem of line integrals, which says that instead of integrating using the parameterization, we can simply evaluate the potential function at the endpoints, which we then do. Yep. And then you plug in. So plugging in plugs into the little f there, and then you do the calculation, and you get the answer. Okay. Right. So another small example. This time the problem statement doesn't ask you, or it doesn't tell you what the potential function is right away. So what you kind of do is you can stare at it a little bit. Maybe what you try to do is you take the first function and you'd integrate with respect to x, which will then give you something close to this, maybe plus a constant. But then you see that by taking the y derivative, you indeed get the y derivative of this does equal x, and so this works as the potential function. In fact, you can kind of be a bit more general about this and say that any function like this, but then plus c some constant, will serve as a potential function. But we may as well let that constant be 0 to simplify things. Okay, right. So yeah, that we have found a potential function. Therefore, big F is conservative. And so this line integral we can do by plugging in at the endpoints, right? So we take little f that we found, we plug in at the endpoints. Little f is this function, plugging it in gives us the answer. Okay. And another quick example. Right. So if you ever see this kind of expression where instead of the vector field f, it's described as nabla f, right, gradient of little f. So that means that you're taking the gradient, and the result is that this is a gradient vector field. This is a conservative vector field. And you're taking a line integral, or in this case specifically, you're taking a contour integral over a conservative vector field. And well, as was stated above, right, in part of this theorem, contour integrals over conservative vector fields are equal to 0 because you take your loop, you split it up at any one point, and then you end up traversing that loop, whatever the point is. I'll just call it capital P, so where P is equal to Q. Well, then you're just doing f of P minus f of Q, which is going to be the same quantity because P and Q are both the same point. You're evaluating f at the same point, and so it's whatever number to minus itself. So it's just 0. Okay. Right. I thought I fixed that typo. Okay. Well, so you might now wonder whether there are any path-independent vector fields besides the conservative ones, because this path independence property was rather nice. And it turns out the answer is no. Okay, in fact, so what this means is that, specifically we have this condition that the vector field is on an open connected domain D. I believe you know what all those words mean. So open means it doesn't have any boundary points. So like on the number line, an open interval would be, it'd have to be open on both sides. On a two-dimensional plane, I'm not able to draw straight, but on a two-dimensional plane, it would have to be a dotted circle. You can't have any of the boundary points of the circle, for example. That's just one possible region. So yeah, on an open connected domain D, a vector field F is path independent if and only if it is conservative. So that's a pretty strong statement there. Right? So all conservative vector fields are arising as, all path-independent vector fields are arising as conservative vector fields. Okay. Right. So now this question about how do we find potential functions. So, right. First, I'm recalling that the cross-partial property is the following. So, if we name the component functions as P, Q, and R, this is one of the conventions that show up in textbooks, P, Q, and R. I forget if the OpenStax book does it this way or not. But yeah, so what you then do is you think about P as being corresponding to the X component function, Q is the Y component function, and Z is the R component, or R is the Z component function. And the cross partials, the mixed partials, are where you end up picking two of these component functions, and then you swap which variable you're taking the derivative with respect to. So when we select P and Q, we then end up doing P sub Y and Q sub X, and those are supposed to be equal. If we pick P and R, then we do P sub Z and R sub X, and those are supposed to be equal. And if we pick Q and R, then we do Q sub Z and R sub Y, and those are supposed to be equal. So all three of these being satisfied is the cross-partial property. And you can sort of see that in so this is in the three-dimensional setting. In the two-dimensional setting, you only have x and y. You only have p and q, which only gives you the one equation here. Okay. Right. The condition guarantees. Right. So I'm sort of emphasizing things a little funny here, but the point is that we have this property, or we know this fact that this condition, the cross partial property, is enough to show that f is conservative if you have one additional assumption on the domain. You need that the domain be simply connected. If you don't have that property, then issues arise, and there's the vortex field is the typical counterexample to keep in mind. So it is a required condition that your domain needs to be simply connected in order for you to then use that implication of satisfying cross partial property implying f is conservative. Right? It's necessary that your domain is simply connected for that implication to be true. All right. And yes, so simply connected, I did mention it in the past, but what I guess I'll elaborate a little bit more now. So simply connected means that your domain doesn't have any holes in it. So that's kind of the intuitive idea. But more precisely, what it means is that if you have a loop in your domain, any loop in your domain needs to be able to be contracted to a single point while remaining inside the domain D. All right, and now some illustrations that kind of show what this means. So you can see that these are simply connected; they don't have any holes. These are not simply connected; they do have holes, and they've been exaggerated extensively. So usually you might have the region instead be like this. But then with a single point that is removed. Okay. But then what happens with that single point is you can kind of expand it. Once you have a tear in your space, you can then stretch it out further and deform it, and you can then make it large like this. So that exaggeration is fine. Okay, and this is what we mean by loop contraction. So you start with a loop, and then the dotted lines are, as you can, or the dotted loops are where you start contracting it down and down to a single point. And in a simply connected domain, it is possible to contract a loop to a single point. Well, it's specifically any loop, not just a loop. Right? I could draw a loop that doesn't circle this hole, and those would be contractible. But loops that would surround this hole, those could not be contracted through that point. You see that if I try to contract this any further, I will pass through that point, and then this loop will not live completely inside of D, and that is the issue. You need to be able to do the process of contraction where every single contracted path is maintained as being inside of D, the domain. And so you hit a wall at that removed point. Right, so that's about being simply connected. Yeah, and so this is just stating it again. So if you have the assumption that the vector field is defined on a simply connected domain, then if f satisfies the cross partials property, then f is conservative. That is the implication that we were after, and we just needed this additional condition that the domain D is simply connected. Now for an example. I think this one's not too bad. Show that it's conservative, and then find a potential function. So this is one of the main examples for finding a potential function. So showing it's conservative is kind of showing it's conservative. Find potential. Okay, yeah. Showing it's conservative, right? So this is using that theorem. So first of all, we check the cross partials property, and here I'm switching over to the other textbook convention, which is that you have the you use the same letter, but then you index the component functions by number, by their position in the vector field. So f sub 1 and f sub 2 are corresponding to those polynomials. Right, and then what you do is you do f1 sub y, or you take the partial derivative with respect to y of f1, which is going to be this calculation, and you get this polynomial, versus you take the x derivative of f sub 2, which ends up giving you this. And you can see that both of these are equal, which means that the cross-partial property is satisfied. And then you also check that, well, the vector field f is defined on a simply connected domain. So it's actually defined everywhere. It's defined on all of R2, which is a simply connected domain. There's no holes in that space. And so by this theorem, this shows that f is conservative. Therefore, there's a potential function, okay, which is the first half of what this example is asking for, showing it's conservative. So now finding potential. So now that we know it's conservative, that guarantees that there's a potential function. Okay. And we just have to find it. So what we do, the process that we take, is, well, we start by integrating things. So the first guy, we know that this is supposed to arrive as the x derivative of some potential function little f. So what we do is we integrate this guy with respect to x. And we'll also then, later, we'll integrate this with respect to y, and then we match these two things up, and we try to make it work. So, right, firstly, we integrate with respect to x, the f sub 1, which is that one, yeah. So integrating with respect to x will give you this. And notice that what I have here is this ends up being the integration constant, the constant of integration. So notice that it's not just a number, it's not just c, but it's actually a function of y. That's because when we take the x derivative, everything that has just y in it, that doesn't have any x's in it, gets killed. It goes to 0 when you take the x derivative, the x partial derivative. And so the integration constant ends up actually being a function of y rather than just a number. And that's going to be important because we have to match these two things up, these two integrals that we're going to take. Okay, so that was us taking the x derivative, or the x integral of f1. Next, we take the y integral of f2, because that's the other thing that needs to be satisfied. This needs to be coming from the y derivative of little f. So we take the y integral of f2, which is what I have here. And when we do that, we get this. And notice that we, again, have a constant of integration, which is actually a function rather than just a number. Okay. So in order to be a potential function for this vector field, these two need to agree, and these two need to be the function f. And so we set them equal to each other, and we sort of match things up. So notice that we have a lot of the terms are already in common. This x squared y is in common, and this xy cubed is in common. And then notice we have this extra y squared on the right-hand side. So that, notice, is going here. And then the last thing we can do is, well, we don't have something corresponding to that, so we would just let that be 0. So we end up getting these two things when we match it up. And so that tells us what the potential function is in general. So notice that we plug in the g sub y, but then we also have a plus c, because for both of these, you can have a plus c in this g of y and h of x. So this is the potential function in general for this vector field. Okay. Where's my mouse? Okay, there we go. All right, next example. So the main reason I have this is because I need an example with 3 components instead of just 2. So, but yeah, the integrals for this are easy also, and the explanation is shorter. So again, what you would expect we do is we integrate the first component function with respect to x, the second component function with respect to y, the third component function integrate with respect to z. So we do all of those things, and we end up getting some partial results. And then we match things up. Now notice that this time around, our constants of integration end up being functions of 2 variables. right? They just have to exclude the variable that you integrated with respect to. So this one excludes the variable x, this one excludes the variable y, this one excludes the variable z, but they can use up all the other letters, all the other variables. All right, the point is that the corresponding derivative will kill that integration constant. So we set all of them equal, which ends up being this rather long-winded expression. But from it, we can play this game of matching up the terms. So yz, you see there's a yz there, and you see that this will fit the yz kind of state. And then you have an x squared yz z to the negative first, which is here as well as there. So that accounts for all of the terms. So you can just let g of x z be 0, h of x y be 0. You could also make them constants, but that's handled here at the very end. Notice that you can't really make them be anything other than a constant, because otherwise that would contribute additional terms in these other parts. So like I couldn't make this be x, because then there would have to be an x showing up here as another term. So that this really forces that g of xz and h of xy are constant, and we may as well make that constant 0. Okay. Right, and this is just to make sure everyone's on the same page, right? So when you are doing this, you are assuming that the potential function exists. But sort of as maybe a first step is that you should check whether your vector field has any hope of being conservative in the first place, which means that you check the cross partials property. This is kind of debatable whether it's better to just go the route of attempting to compute the potential function first without really checking that it satisfies it. For me, or really for like simple problems, when the problem is simple, usually you can just stare at the vector field and kind of arrive at the potential function just by integrating things in your head. When it's more complicated, then the process of determining the potential function may end up being more difficult to do, and you might need to actually write things out. And then you maybe get to the point where you're not certain, or you can't just immediately see that the vector field has a potential function. And if you're not able to immediately see that, then maybe in that circumstance it's worthwhile to check the cross-partial property first, just to verify whether f has any hope of being conservative at all, right? So if you end up getting some complicated looking vector field, and you can't tell right away whether it has a potential function, one strategy to take is that you check the cross partials property, and if it turns out that one of those three equations, if one of where did it go? If any, where did it go? There. So if any one of these three are not satisfied for that given vector field, then you know right away that the vector field has no hope of being conservative. It is definitely not conservative. Okay. So that can just be a useful check to make at the very beginning of your computation. And for me, I would only recommend it if the vector field is sufficiently complicated that you can't just find the potential function in like a few seconds. Yeah, so checking that is good. Yeah, okay. But again, just because you checked it doesn't guarantee a potential function. You also have to keep in mind the domain, right? So if the domain is simply connected and it satisfies cross partials, then yes, it is actually guaranteed by a theorem that the potential function exists, and then you should go ahead and try to find that potential function, spend that effort to actually integrate things and set terms equal to each other. All right. I think this is the last bit that I have, the vortex field. So this is just a key illustrating example of what we are describing. So This is an example of a vector field that satisfies the cross-partials property, but is not conservative. Right? The key example to have in mind. So the vortex field is defined by this, which, oh, I typoed there. That should be an x squared and plus. All right, the same denominator as here should be there. So this vortex field, which I gave last time, I'm sort of repeating it again. So the cross-partials property, you can first check that it is satisfied. This is one of the things that we wanted of our sort of counterexample. So we wanted that the cross-partials property is satisfied, and if we take these partial derivatives, we do see that that's the case. So notice that when I take the x derivative, I have to do a quotient rule. I've explicitly written out how the quotient rule works. This just means you're taking the derivative with respect to x. It's just an abbreviation of let me maybe change colors. It's just an abbreviation of partial x, right, d dx. Right. So yeah, so that's the quotient rule, and I'll give you this quantity. And then same goes with the y derivative. The top and bottom are both functions of y, so you need to do quotient rule. You go ahead and do the quotient rule. You get the same result. Okay, so cross-partials property is satisfied for this vector field. But now we're going to use this other thing that we know about conservative vector fields, which we've discussed in this section, which is that conservative vector fields are supposed to equal 0 over a closed loop, right? So for conservative vector fields, you must have that this equals 0 for conservative vector fields. Let me just abbreviate it for conservative vector fields. Okay, and we check that this doesn't hold true for this function, or for this vector field, by setting up, by choosing a contour that circles around the singularity, the point that doesn't lie in this vector field. So notice that this vector field is not defined as 0, 0. Right? If I try to plug in 0, 0, I get division by 0 errors. So this vector field is undefined at the origin. And then we just take the parameterization about the circle, the unit circle. So there's a hole there, which I'm okay, and you instead end up taking this contour in this direction, and I think you may as well start at this point, right? So that's what this contour is doing. So we parameterize the unit circle 0 to 2 pi. The parameterization is cosine t sine t. And then we compute the line integral explicitly using the parameterization. So this, when you plug things in, right? So plugging into f, I guess that's actually a little bit of a calculation to do that. If you were to, let me look at it from here. So, oh yeah, I see, that's easy. Yeah, so cosine and sine, you end up plugging it into f. So now these functions here, these are the parts of f. So this is f sub 1, f sub 2. These are the components for the vector field f. If I plug in that, the denominator is equal to 1 by the Pythagorean identity, trig identity. So you just get cosine and you get negative sine for something's reversed. Oh, I see. Yeah, okay. I reversed them here. So this is actually f sub 2, this is f sub 1. Okay. So yeah, then when you plug in, this is f sub 1, so you get minus sine, and this is f sub 2. When you plug in, you get cosine. So you do get this order. Right? These two lines should be like flipped. And then dot product it with r prime. Well, r prime is easy to compute. You get that. You take the dot product, and you end up getting the value 1. Okay. So this line integral, this integral over this loop, would expand out to this, and you're integrating the function 1 from 0 to 2 pi. I normally like to put 1 here. Textbooks don't like to put 1, but I do. And then you do the integration, and you end up getting the value 2 pi. And, well, that's certainly not 0. So this violates the property that conservative vector fields have, which is that they are path independent, right? If this vector field was conservative, it would have to be path independent, which would mean that the line integrals over loops would have to equal 0. But we don't have that. And so the reason we don't have that is because this vector field is actually not conservative. Right? Yeah, and the whole point is that, yes, this the key explanation for why such a thing is can occur is because the domain of this vector field, it's not defined everywhere. There's a singularity. There's a hole in the space. Okay. I guess that's all I have for this topic. So